in Cosmos, when you want to interact with the chain, you're going to do that via a transaction. Transactions contain all of the data to validate, to pay for, and to include what request you have for the chain. Let's go over that now. Here on the screen, we have a default transaction JSON blob. This includes all of the data such as the messages. You can think of a message as an action, a specific action within a transaction. Then we have the memo, which will include any arbitrary data that we want to include. This can be used within our application for searching for certain transactions to see if they've been sent by a user, or in the case of centralized exchanges, they'll give you a random string of numbers. You'll attach that here, so whenever you send it to them, they can verify that that is for you and then move those funds to your account from the bank sent. We have a timeout height. The timeout height can be used for allowing for a transaction to not be processed after a certain time and can be canceled out. So maybe we submit a transaction with a very low fee, we wait for a validator that accepts that fee, and if one does not accept it by, in this case, height 31, we want to actually cancel out of that transaction, and we'll submit a new one, or we'll do something on the other side. And then we have some extension option information here. The other information that this contains is the auth info, and this includes things like fees, the gas amount that you want to do. So again, as in a previous video, we went over what is the gas limit, how do fees, all these things go over, so you can check that out if you have not seen that already. But then on top of this, we can also allow for other accounts to grant and also for us to pay for transactions through other accounts. So in Cosmos, we can use the fee grant module to allow for an account or a smart contract to actually pay for our fees on our behalf. So maybe we don't have 500 extra Juno after we've already sent these tokens, that if that other account does, and that other account has granted us, in this case the from address, access to be able to use their fees, we can use those as the fee payment here, and that would be included within these two sections here as the actual address of those accounts. Then finally, we have the signatures tab. This is going to be where whenever we sign the transaction with our private key, which is done via the CLI or via your Cosmos.js front end, it will get put into here to verify that we indeed do own that from address, so we aren't trying to spend other people's money. You can only spend money for the accounts that you actually do own. Within this, let's go through messages a little bit deeper. So a message, as I mentioned, is a singular action that we want to take. In this case, we want to do the action of sending our native bank tokens, in this case, Juno, and some other token here that could be on chain, and we want to send that to this other address here. So again, we have our from address, that is who we have that key, we have that mnemonic, whether that be in our wallet or via the CLI as a key, and we want to send it over here. Now, many developers think, I want to run multiple transactions per block. So can I submit this transaction, and maybe I want another one that does, say, another bank send or a message delegate or an execute on the contract. And you could do this in multiple transactions by increasing the notes of the transaction, and you can get about 20 transactions in per block per account, but it's a much more efficient if you actually run multiple actions within your single transaction. This can be done easily just by increasing the amount that is within the array. So if I wanted to send to this other account, in this case, we're just going to do some A's here, just as an example. And maybe I want to send this account some more tokens. So this one will get 10, and the other one will only get 1, and then 1 of this other token. This would be a valid transaction, so long as this address is actually real. The issue could arise in terms of you not having enough funds. Maybe you only have 10 of this token, and we'll just assume that enough fees here. So you only have 510 tokens, but you're trying to do an action, a transaction of 500 plus 10 plus 1. So 511 tokens, but you only have 510. Your messages are going to process one by one until one of them does fail. So in this case, we're going to count off the 500. So now you have 10 tokens left that are in your wallet. We're going to go through this first one. We're going to assume that this is successful. This is a valid account that you're sending to. The from account is correct. We're going to subtract 1. Now you have 9 tokens left. We'll ignore this other one for now. This is not needed. Great, so we have 9 tokens left in our balance. Now the SDK is going to verify the next one. So we're going to try to process this, and it's going to fail. As soon as this fails, because we only have 9 and it wants to use 10, it's going to start reverting these. So this action is going to be reverted. Then this action is going to be reverted. Then the entire transaction is going to fail. Why? These transactions are not atomic. The SDK will have support for atomic transactions in the future, where maybe the first one was successful. If that's great, the next action can fail. Currently, that is not possible. So all messages must pass, or else all will fail if one fails. So in this case, we would receive our funds back. No funds are lost here. Everything is back into your account as normal as if you had not done anything. You only will lose out on the fee. Why would you lose out on the fee? Because you tried to submit the transaction and you already did use some compute to process these values here, the chain is going to take away your fee. Again, this is a small amount of fee, but if we did not take that away and these failed, you could just submit a lot of transactions where we could just submit a ton of these, cause a bunch of compute costs on the infra side, and then let's just say the last action fails, which in this case would be a message. We know that the infrastructure would then have done all of that compute time for it to not even receive anything. So it's important that chains do charge you for even failed transactions, or else it could be an attack vector to DOS the chain, which is not very good for public blockchains here. For now, this would fail. You would then need to resubmit your transaction for, in the case that we had 510, we decreased this to 9, now this would work. There are more efficient ways using a message multi-send through the bank module if you wanted to, but this is just to give an example of other transactions that we could have here, such as like an execute contract. If there was an execute contract here via the cosmos-sdk module, and it had all that data, we can do a send and a message transaction here all within one, which is super convenient. In the next video, we'll go over how decoding transactions work, how transaction hashes are resolved, but in this case, we're just going to go at a high level. We're going to see the transaction was submitted at height 32 here. So we've done a bank send and it happened at height 32. If we compile all of the raw bytes of the JSON transaction back from this page, we can get a transaction hash. This is just the SHA-256 of it. Again, this will be in the next video to describe some more. Here we have code. This is an SDK response code. So 0 means the transaction was successful. There's other codes that can be found in the cosmos-sdk repository that return other data. For example, if you didn't have enough fees, or maybe the sender is incorrect or something along these lines, this code will be non-zero. So if you want to verify that a transaction was successful, you can typically check for code 0, and then usually you can also check for the raw log on the transaction hash response. In this case, it's full, but sometimes it'll be empty, which also could mean, there are other issues there, so you can check between these two things. This data here is a hex encoding of the type of transaction. So in this case, it would be a bank send transaction. You could, pull this out depending on like gRPC requests as you need. Here within the raw log, it's just a JSON format of all of these values here that we see in the standard log. So this is going to include some information such as what events have run. This is great for finding out what's actually happening underneath the chain, and also for, say, tax reasons, where we can verify the events here and add those up for users and then export that to a CSV and something like stake.tax, which is very convenient at your end of year tax reasons. So here we see it's a message send, who's the sender, and what module are they using. Again, this is a bank send, so it's going to use the bank module for this singular action. We can also see the underlying events that have happened here, which are broadcasted under the SDK. So in this case, the coin spent, we spent 1 Juno from this account. So we're able to see that here within these raw log events, and we could parse through these, and then we can see who received those tokens, and we can see that via the event stream. And then also here, here's the transfer type and what message and who was that sender. It shows how much gas was wanted. So we were willing to pay 1, 2, 3, 4, 5, 6 gas, but actually used was significantly less here, about 62,000. Now, as we add more messages, if we double the messages, this wouldn't increase to say 161, like this would, or 120,000. This would not increase like that. As you add more messages, it's actually more efficient in terms of that. As we add more actions to our transaction, it's more efficient because we don't have to compute all of these other values here. So we don't need to run all that logic over again. We can just run the logic specific to each module, each action that we're asking to perform. So these values would not increase exponentially. They increase actually a lot slower relative to that, because a lot of this gas use was for the other parts of the transaction that only need to be run once. Then if we run through here, we can see, this was a transaction. Here's what the body was. Here's what the actual memo was. Here's the signing info. So what is the account's public key? Whenever you do your first transaction, this is saved on chain, so we can verify that these wallets are linked. Here's what that transaction was. This was the first transaction on the chain, so we use a sequence of 1. And this is automatically done behind the scenes for us on the CLI by querying the chain, hey, what's our sequence? Now again, if you wanted to run multiple transactions within the same block, you would need to modify this directly and say, 2, sign that transaction. This will be done in a future video via the CLI. I want to also sign 2 and submit this at the same time with 1. You can only submit 1 sequence at a time per block, but if you wanted to submit multiple, this is how you would do that. And then we can also see here the signatures tab. And so there's our account signature there. It includes some other information like a timestamp, and then here's some more events again that we had gone over previously up ahead. So this is what is within a transaction and the data that is returned back from doing a single message. Now let's go over multi-message transactions in more detail. Here's an example of doing a message smart contract with the same contract, but this shows that we want to mint a token, both 1 and 2 at the same time. And so we can do that through a single transaction with multiple messages. So we're going to do this with this token 1, this one for the token 2. If one fails, they all fail, and we can verify that, fix up whatever's needed, whether that's not enough fee, or maybe we missed one of the validations here for, say, token URI. And so we can push all these through here. This is how you would sign it in the CLI. We can see that you just sign that message with the information such as your from key. This is going to add that signature as well as the extra signing info. We're then going to broadcast this new message that has your signature in it to the chain. This will return a transaction hash, and then you can just query this to get all of those events that we just went over. You can see here how this could be useful if we have a lot of different NFTs, for example, that we wanted to mint against a singular address or multiple addresses, depending on your use case. Where here's a basic Python script that's going to start at index 1. We're going to supply it a CW721 cosmos-sdk contract. This is an NFT contract. We have already uploaded it to the chain and instantiated it, and it returns back this value. This is that instance of that smart contract. Here's our owner wallet. This is who is the admin of this contract, who is actually allowed to interact with it, to mint tokens, to do those sorts of things. And then here we're going to have just a bunch of random IPFS links. This is up to you on a CW721 of what you want here within the smart contract. Here we have the basic format for a transaction, as we just went over, the body, the authentication info, and some of that data so you can modify this to your needs. But the most important part is going to be these messages. So we can iterate over all of these links here. And then within the message body, we're going to append this message execute contract with all of the specific data here that we need to mint these tokens. So as we add more values here, it will just persist within the messages. It will then dump that out. We can then sign that, and then we can broadcast that to the chain. So this is the programmatic way of performing a very large amount of actions on a specific contract, but doing it all within one block. And if one fails, they all fail. So it's very convenient. You can write this out in any language. It's just a simple appending of these different messages for a very efficient experience.